I didn't do it.
Yeah.
I got 16. I just need to know if you're doing it the negative 1 half. Release form. 1 half. Release form.
I took the inverse left on the derivative.
Oh.
Did you guys do product rule?
Yeah.
What's the U prime? Just one. Did you come over here and say F inverse has the point of 40B, which means F has the point of, you set 40 equal to the nastiness, right? 2x square root of x minus 6. Who found out what that was? 10. Messy, right? Now, I think the book went a little bit harder than AP's. I've never seen them go above 3 or negative 3. But, alright. How do we solve it? I guess you could have actually squared both sides and probably set up a quadratic. That's why the number is bigger. Yeah, Katrina.
What happened to the square root of 6 of x minus 6 times 2?
Right here, I'm just setting 40 equal to the original equation. Over here, I was doing product rule, so second, square root of d first times 2 plus first 2x d second. This is x minus 6 to the 1 half, so I brought down a 1 half. Negative 1 half makes square root in the denominator times u prime is just 1.
So you said that 40% original?
Yeah, to the original. Then, my one's not working out somehow. How do we finish? I'm not even simplifying because I'm like, whatever, I'm just going to get a number and then figure it out. So you could have simplified, I suppose, if you really wanted to. I need an x up top though, right? My poor little x needs to be up here, 1x. So I plug in my 10. Because it's a b, so I plug in a 10. I plug in a 10. What's 10 minus 6? 4! What's the square root of 4? 2! So write 1 over 2 times 2 plus, oh, where did I not plug in my 10? Yeah. 10 goes up there too. Plus 10 over 2, square root of 4 is 2. So 2 times 2 is 4, plus 10 over 2 is 5, 1 over 4 plus 5 is 1. Now pause. Even if you weren't able to beat me, in your groups you should have been talking about things like how do you find the derivative of the inverse? What is the prime of? Not 40, wait, we need to take 40 over here. Alright, let's take 40 set equal to, there is some problem solving there. Then you just say, wait, we need f prime. Product rule, guys. Hopefully those conversations were going on, even though it was a kind of crazy problem. Original function equal to the number in advance. Well, I mean, I guess you could do product rule first and then do, they're two separate steps and then we put it all together. Does that make sense? So I kind of did the product rule first because I needed it, but then I also need the number to plug in, so I did that part too, and then I put them all together. Good question. Where'd you guys get stuck? Who got stuck, like your groups got stuck in the product rule, like just something went wrong? How many groups got stuck in the 40 equals?
You got stuck.
At least for a while, that slowed you down, right? Yeah. The square root, like the plugging in, there was a lot of places to get stuck. But do we understand the process? Start, go ahead.
Oh, okay, so that's 10 over the square root of 10 minus 6. How would you write that without, like, the fraction
You would have multiplied top and bottom by the square root. So then you would have had to distribute. Oh, this one could have been, what's another way of writing that? Up here. You could have rewritten the derivative. I think that's what you mean, right? Like another way of showing it. This could have been 2x times 1/2 x minus 6 to the negative 1/2 times 1. But the problem is our brains don't think in negative 1/2 powers. You see why we wrote it this way? Because then it's like, oh, a square root in the denominator, I can do that and I can like get there easier than negative 1/2 and then rewrite. Was number 89 hard? Yes. It was a little rough. Number 90. Did you guys get that far? How many groups started number 90? How many groups finished number 90? Who started number 91? Finished number 91. Let's go ahead for sake of time. Let's go back to homework. Let's grade the evens. Tomorrow, maybe we'll come back and then we'll get to revisit this. For those of you guys that didn't get to attempt 90 and 91, did you at least write the question down? We'll come back to it and talk through it a little bit more. There's only one full group that actually got to play with it. So for sake of time, we're going to pause. But if you guys want to play with these, this is right at the end of notes for section 2.6. That's about where we usually do it, which is homework number 15. But we'll come back to them.
Which homework are we grading right now?
We are grading 14 and 15, 2.6a and 2.6b, the evens. 2.6a and 2.6b, the evens. There were some evens, there were also some odds. We're just going to grade the answers real quick. I think Slater has a lot of these online too, but...
They don't have to.
Oh, interesting. Okay. But they have other sections? I don't think people like these sections. Interesting. See, you're in good company. The world doesn't like it either. Okay, here we go. Ready? Our first even was number 2, yeah? Final answer, guys. Especially in this homework. Final answer. Kiddos, I record this. You can look at it online, okay? We're just going to go fast. But my guy's grading. We're just going to write down the right answer. If you got it wrong, write down the right answer. You can look at the video. You can pause it. You can see the work, okay? So, number 2, our final answer is negative 1/6. Number next even. Number 8. Final answer is negative 2. It's okay. Write it down. It's okay. Write it down. Mistakes happen. Mistakes happen.
What?
Write it down. Negative 2. Number next one. 10. Final answer 4. Wait, are you guys checking to make sure it's the right problem? I haven't seen that these answer keys are wrong, but same problem, right? Struggle. 4. Number next one. Negative 1/4. Negative 1/4. 20. Final answer 1/8. 1/8. 72 is next?
Like one to look at the graph.
Oh, okay.
I forgot to plug in.
I mean, aren't you just doing the reciprocal slope?
Yeah.
So then if the slope of 1 is 1/2, Katrina, of the original, the slope of the inverse is going to be 2 instead. Because remember, the slope of the inverse is 1 over the slope of the original.
How are you supposed to find it?
Oh, I found it.
Just give you a graph.
Hold on, don't touch the meter.
I told you the slope.
I got it.
Yeah, the slope.
So it was at 1, 2.
Yeah, and then you put 1 over 2.
They gave you 1/2. All right, we'll have to come back to it because you guys aren't giving me clear information whatsoever. Number A, letter A is 2. Letter B is 1/2. Letter A is 2. Letter B is 1/2. I'm gonna have to look at it because you guys aren't clearly explaining. What's the number next, Ethan? That was it. So let's go ahead and where do we start for 2B? Nope, we're in the wrong section.
I have.
Come on. Okay, 24? Yeah. 24. 2t over square root of 1 minus t to the 4th.
Oh my god.
I got it right.
Is that a good feeling?
Yeah.
All right, good. Number next one. 28. 1 over 2 root x times 1 plus x. 1 over 2 root x times 1 plus x. You guys getting the right ones? Go ahead and write them down if you need to. Number next one.
34.
Got it? Negative 1 over absolute value of x, square root of 9x squared minus 1. These are going all right? Good. Negative 1. Got it? Number next one. Okay, hold on. Derivative. 1 over x square root of 16x squared minus 1. Plugging in the point, it was a little bit messy. One version is 2 root 2. One version is 2 root 2. Or you could have done 4 over root 2. That would have been fine too. 4 over root 2 is fine as well. Tangent line, you guys did not have to simplify. Look at the point slope. Y minus pi over 4 equals either 2 root 2 or, remember I said the other form of that could have been 4 over root 2. They mean the same thing. So then that could have been in this spot as well. Okay? That could have been in that spot as well. Number next one. That's it. Okay. Kiddos, on the inversey one, we might have some questions. I'm tracking, all right? Let me go ahead and tomorrow, when you first come in, I'm going to have 90 and 91 on the board, okay? And I'm also going to have up your textbook open to 2.6a, and we'll hash out, we'll probably get people up to the boards, like literally. We'll just get people up to the boards. They'll show us their work. Those who got them right, you were able to check it today. Sound good? Some extra credit participation never hurt anybody, right? Okay, so tomorrow, 2.6a, I heard that we were just like groaning all over the place. But some people were like, oh, I got some of those right. So we'll get their work up to the board, extra credit participation. And then while they're working on the boards, you guys can be, those of you that did not finish today, which was the majority, can be working on 90 and 91 in groups. Sound good? Okay. So be ready for that. For right now, though, 2.6b was definitively better than 2.6a, which I totally expected. The formulas were hard, but you were plugging and chugging. There were still mistakes that could be made, but you were plugging and chugging. Let's go ahead and get back into our notes because we do need to start 2.7 today. But the nice thing is there's no pressure on finishing because look at the backboard real quick before we get ourselves the timing. Okay, things are weird and let me explain why. Remember how I said next Wednesday is the PSAT project lesson? So we can't have a test next Wednesday? And I said maybe we'll cram it in on Tuesday, but then I just executive decision we're going to have the test on Thursday. What does that mean? Non-PSATers, my seniors, they have an extra day of review. Which I'm not going to be necessarily teaching them underclassmen. They're going to have a work day. Okay? So underclassmen who are taking the PSAT, they're having a work day. I know it's going to be hard. You're like, I wish I had a work day. Yeah, but the PSAT's important. Seniors can tell you, like, they're in the midst of college applications and figuring out what colleges will take you, et cetera, et cetera. You want to be able to get those SAT scores up, right? Good practice. It's an important activity. They had to do it too. And just think of it this way. You have an extra day of studying for your test, an extra night. So underclassmen, I do apologize. I can't give you an extra work day, but you do an extra day of Listen carefully. So we're starting 2-7 today. Working on 2-7 tomorrow. And very possibly we might be working on 2-7 on Monday as well. I have 2-7 right now due on Monday, but realistically it's probably going to be due on Tuesday. Uh-oh. Which means 2-7 might be a little rough. But I need you guys to go into it actually realizing that I think for the most part on the AP, the concepts of 2-7 are easier than the problems in our book. Okay? That's number one good thing. And number two good thing, out of all the word problems the AP can throw at you, my favorite, and what I think is actually the most formulaic, the most systematic, the most just do this, 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 and you're done, are the problems in section 2.7. I think they're better than motion. I think they're better than optimization, which you haven't seen yet, linearization you haven't seen yet, differentials you haven't seen yet. I think this following one is one of the easiest, but you have to get it down and you have to figure it out. Before we get into that, I know there's like a page in here. This page is basically saying like, hey, your book actually has good information. Long story short, before we go into section 2.7, this kind of talks about all of elementary functions, who they are, what they are, talking about the derivatives of elementary functions. If you realize this is like around the 1600s if we were looking at it. All of the derivatives of elementary functions were found by this time. And elementary functions include polynomial functions. Oh, like quadratics, cubics, etc. Rational functions. Oh, like numerators, denominators, f of x over g of x. Radical functions, or functions with radicals. Logarithmic, exponential, trigonometric, inverse trigonometric. Guess what? You've derived all of them. And most of nature is modeled with these elementary functions. Now, there are a few things in physics. There's like an asterisk if you read it that are with non-elementary functions. But you have learned all of the differentiation rules for all of the elementary functions upon which, I don't know if I want to say nature is based. I'm not sure if I believe that nature can be modeled. Anyway, it's pretty spiffy, it's pretty snazzy, and some of you might want to go check out this table because this is like all of our forever card rules in one place. It's a pretty good one. But if you guys notice, how many U's are in this page? A lot of them, right? Instead of the derivative of sine of x being cosine of x, they have U instead. Am I in good company putting U's instead of X's just so that we can generalize in case it's something other than X? So we see a lot of times U primes around here as well. Is there any rule that we don't have in a forever card yet? Rubber number 18.
It's just
Just
one
that one?
equation?
What? Easiest one ever. We talked about it in homework. It was introduced in a homework. It was never taught.
Actually,
It was never taught, huh?
it's like actually the view.
It shows up as kind of random. But when it does show up, this is going to be a lot easier if we just have a card on it.
What's it called?
The absolute value function, the derivative of absolute value functions. Forever number 18. It'll be on my PowerPoint. I just haven't been able, sorry, my Google Slides, the form online. I'll update it for you guys so you don't have to stress about it. But that one's going to be our next forever card. All right, with that, we go into section 2.7. Sorry, were you guys still looking at it? A couple more seconds. Close your time. It can actually show up in two forms. It could be U over absolute value of U. It could also be absolute value of U over U. It means the same thing. The meaning is still completely intact. The absolute value could be on the top or the bottom. Basically, Ryan, by memorizing this, it just makes it so you don't have to go to a piecewise function and then take the derivative of the piecewise and then come back. So it just simplifies it a little bit. But everything else we have. Now guys, isn't this a huge accomplishment? Look at all these formulas. If I showed these to you last year, wouldn't you have been like, oh my goodness, calculus is ridiculous. Now you're probably still thinking that. But isn't it better that we take it little chunk, little chunk, little chunk? Okay. Knowing all the derivative rules, that's a huge thing. You can derive any elementary function, just some of them are harder than others, but you have the tools. Just need some more practice. Section 2.7. You do not need to write this down. Go ahead and start at the beginning. Related rates start by saying, hey, you're gonna have to use a couple tools that you've already learned. One of them being chain rule, and one of them being implicit. To be honest, implicit is chain rule. Because implicit just says, hey, the derivative of y is dy dx. Example. Just because we talked through like a few fun things. Before you guys leave, Ella, Laura, Katrina, and Caroline, I have your test. Test corrections are worth 1/3 points back. Not 1/2, so we have to wiggle you guys off. Alright, remind me real quick. Chain rule says what? Come on, amazing one. Chain rule says what?
Take the derivative of the outside chains
Good. And if it's in terms of this one, there were 3 different ways of writing it. And technically, for some of you, visually, it might be nice to think about even though we didn't show it earlier, like boxes. Maybe it'd be nice. You can say derivative of the outside, keeping the inside the same, times derivative of the inside. Or if you like it better, you can say outside box prime with inside still there times inside box prime. If you like the visual things. What's going on? What's going on? Implicit differentiation. What on earth? I'm going to write this kind of weird in a way that you probably actually don't expect. So what if I was to do something like x squared plus y squared equals 5. Wait. That's not what's weird. You've seen things like that before. What if I take the derivative? Let's see if we can figure this out. With respect to t. This is weird. That's getting you ready for related rates. What if I take the derivative with respect to t? Why on earth would t be important in real life? Time. Struggle. Getting real life stuff. If things are moving and changing, they're moving and changing based on time. Miles per hour, feet per second, meters per second. Inches squared per minute. Pause, do what you know. Derivative of x squared. 2x. Struggle. Do these variables match? So then can we put it together? If they don't match, shouldn't we have an extra u prime? And who would he be for x? dx over, use the variable instead, dt. This is weird, but it's an application of implicit. Whenever the variables don't match, which we're used to with y's, but this time x doesn't match either. All right, fine. So we do a d of this term, x, over that dt. So what would it be of y squared? 2y times, they don't match. Now this one should make a little more sense. It's like dy dx, but we're not doing dx, we're doing dt. So think, well, if y needed 1, well, x needs 1 too, because he doesn't match the t either. And we can still say, as always, the derivative of any constant is still. This is an application of implicit. What's weird is, there's another variable called time. What's weird is there's another variable. Now, let's go ahead and look at this box. But first, the intro question. In one situation, in one scenario where something is changing and moving, with different quantities changing and moving, are they changing at the same rate? Now, let's look at our scenario. You're filling an inverted cone with a fluid. Question, what's changing if you're filling an inverted cone with a fluid? Imagine it's one of those like snow cone cups and you're like at a water cooler. Okay, you're filling it up. Volume. How much water is changing? What else is changing? Let's not go into mass, we're getting a little too physicsy. What different dimensions, what different quantities? Surface area, like the circle on top, isn't that getting bigger? Okay, well if the circle's getting bigger, what are some parts of the circle that we've talked about before? The radius is getting bigger, the diameter is getting bigger, the circumference is getting bigger, and what else is getting bigger? The height of the water in the cone. Right? Make it go too long, it's going to start spilling out and then you're in trouble. Okay, my question is the radius, the diameter, the height, the circumference, the surface area, the volume, all changing at the exact same rate? Why is this a hard question? Because it's one thing. Water's filling up. Whatever. Wait. What are units of volume? Give an example. Meters.
Oh, I get you.
Or if we're talking about volume in the sense of like base times height, area of the base times the height, it could actually be something like inches cubed volume, right? Well, if volume is inches cubed, question, what would radius be measured in probably? Inches. Wait, can you have inches cubed be moving at the exact same way that inches are moving? No, they're different rates just by the units alone. And then the surface area, well, what's an area measurement? Like inches squared. Well, inches squared and inches cubed and inches can't be all moving in the same way. Now, is it one scenario? Yes. But are all the different measurements changing at all the same rate? No. And let me show you a quick demonstration of that. If we were to do a lab, which we're not going to do, I wish we had time. It would be really super cool. I totally admit that. But A, we would need better instruments. B, we would need time. And C, we would need people actually willing to carefully measure stuff. Hold on. Where is he? Nope. Nope. There he is. If you guys notice...
No.
Why isn't it? You're killing me, Smalls. This is awful. Is it gonna work? I have no idea. That's fine. Okay, I think it's gonna work. Alright, let's say someone else did the lab for us. And as they did the lab for us, this doesn't work. I can't speed it up or slow it down. Come on. Nice. This is the water right. This is showing us the changes in. Now look, volume is changing by, oh my goodness, by like 0.3, man, it's changing, it's actually changing at different rates because there's different increments. The question, if this one's going from 0.001 to 0.01, is that the same as this one going from 0.04 to 0.16? So the height is changing or increasing in different increments than the volume is changing or increasing. And to be honest, you guys see that it's slowing down?
Yes. Because it's harder to fill it down.
Something like that. But if you're looking at it as the different increments are changing, did you guys see how these numbers are not changing in constant intervals? Number one, they're not changing in constant intervals, so it's not a constant rate. The rate is changing. Does that kind of make sense? Like that it would fill up faster down here than it would up here? Doesn't it take more water to fill the space as it starts to broaden out? But I need you guys to realize that even though this is one scenario, the water is filling the tub, the rates of the height and similarly the rates of the radius and the circumference of the surface area are not the same as the rate of the volume. So the rates are different and yet related. Oh my goodness, what's the title of this section?
Related.
Go team. So, what if we were to go back to our notes and I need to go bring my computer?
Sorry.
No, you're good. And what if we were to ask the question, well, how can we relate the rates? Is there anything that we know that could actually relate them? The answer is yes. If you want to know the relationship between volume and height, let's say radius. Is there a formula that we already should know, or at least have seen before in our lifetime, that relates the quantities, not the rates, but the quantities, volume, radius, height? Yeah, V equals. There's a geometry formula. We got this, right? So V equals, now we might not remember it, but theoretically we've seen it before in our lifetime. So you know the volume of a cone.
Pi R H cubed.
Pi R, area of the base, pi r squared, H, wait, times 1/3. Sorry, they threw me off. Hold on. Wait, what does this relate? Volume, radius, height. But we need rates. Take PET at both sides. Get out of here. We'll see you guys tomorrow. Work on your test corrections tonight. You're not going to get into tutor tonight. No. Here's your test corrections. And those of you behind, get on up. If you're struggling, ask for help.
I think it's a good thing. Seriously.
Laura.
No.
Caroline.
That should be hard.